The Department of Mathematics, St. Xavier's College, Kolkata. The Department of Mathematics. I would like to thank everyone present here today for taking. I would like to thank everyone present here today. In the last 2 years, our world as we knew it has changed drastically. The coronavirus pandemic has adversely affected the lives of millions across the world. As the entire world recovers from the blow of the Omicron variant of the coronavirus, we look forward towards a brighter future for all of us gathered here today. It's said that the night is darkest just before the dawn. With that in mind, the Department of Mathematics at St. Xavier's College, Kolkata continues on its relentless path to impart knowledge and change lives. In these times of despair, we have all looked towards the light of knowledge to guide us. As part of this endeavor, St. Xavier's College has been an active participant in spreading knowledge and ensuring growth academically, personally, and professionally for all its students and faculties throughout these tough and testing times. As a tribute to this recognition, I feel proud to say that our college has been ranked 4th by the National Institute of Ranking Framework, Government of India. We have gathered here today for an international webinar presented by the Department of Mathematics. Our webinar today would focus on simple mathematical models for evolutionary rock, paper, scissors in side-blotched lizards. Differential equations, as we know them, explain several natural phenomena accurately. Side-blotched lizards exhibit a unique form of polymorphism based on 3 distinct throat colorations, and each color-based subpopulation, or morph as it's called, uses a different mating strategy. Interestingly, the interactions between these morphs leads to an evolutionarily stable rock, paper, scissors mechanism, where the percentage of these 3 morphs fluctuates around the 1/3 of the population. Typically, the least common morph in one breeding season often has the largest number of living offsprings in the next year. Now, here is where things get really interesting. The evolutionary behavior of side-blotched lizards can be modeled as a simple, discrete dynamical system. The shortcomings in this discrete model can then be addressed by transitioning to a continuous model of 3 coupled ordinary differential equations. Using the principles of calculus and linear algebra, this talk will focus on the process of developing mathematical models that fit the fascinating sexual selection mechanism that leads to the evolutionary balance in these morphs. To illuminate us on this very interesting topic today, we have as our speaker Dr. Arup Mukherjee from the Montclair State University, New Jersey, USA. As we traverse through this webinar, I'd like to tell you some housekeeping rules in general. Everyone present with us over Zoom is requested to keep their audio and video off during the entire duration of the webinar. I request everyone on Zoom to ask questions only through the Zoom chat box. Everyone present on YouTube with us is requested to ask the questions through the YouTube chat box only. We would be answering the questions only at the end of the webinar, subject to time availability. I would once again like to thank everyone for being here today. With this, I would heartily like to welcome our principal, Reverend Father Dr. Dominic Savio S.J. Father has always been a source of tremendous inspiration for all the students and the faculties. It gives me immense pleasure to say that Father Principal has been awarded the Shiksha Ratna Award 2021 by the Department of Higher Education, Government of West Bengal. With this, I would like to call Father to grace us with his presence, deliver the welcome address, and initiate our program. Over to you, Father.
Thank you. Thank you very much. Very good evening to all of you present here, and very good morning to Professor Arup Mukherjee. Thank you. Thank you very much. First of all, I'd like to thank the Department of Mathematics for organizing this seminar with Professor Arup Mukherjee. As I welcome all of you to this international webinar on the topic, Simple Mathematical Models for Evolutionary Rock, Paper, Scissors in Side-Blotched Lizards, organized by the Department of Mathematics, St. Xavier's College, Autonomous, Kolkata. I would like to extend a very warm welcome to the guest speaker for today's webinar, our alumnus, Professor Arup Mukherjee of Montclair State University, New Jersey, USA, for joining us to share his knowledge on this curious topic. We are very, very grateful to him for making himself available for us for this international webinar. As explained by our MC. A mathematical model may help to explain a system by a set of variables and a set of equations that establish relationship between the variables. Side-blotched lizards are popular for achieving a dynamic balance among its three morphs, such that any of the three do not get eliminated. The interaction between the morphs generates a self-sustained polymorphic population that divides the population into more than two sharply distinct forms of a single species. Surely, see, of course, I cannot, talk much on this model. I'm sure that we have a great person, Professor Arup Mukherjee, will enlighten us. I take a great pride and delight in addressing this webinar of the mathematics of the department. The department continues to produce bright and dedicated students who consistently stand out and excel. We have a great example of our own speaker, Professor Arup Mukherjee. Notwithstanding the COVID-19, the department has organized several webinars for the students and the faculty members as well. The virtual mode of learning does not arrest enthusiasm and passion, as the need and joy to understand remains. The scope for communication today allows us to hold this international webinar. We are grateful for its possibility that can heave the progress that is ambivalent due to the pandemic. I congratulate the faculty members of the department headed by Professor Charita Roy and all the faculty members, our enthusiastic students for organizing this webinar splendidly. I feel assured that the webinar will be well accomplished. These few words, hoping that the light of knowledge continue to shine on each of us. I wish this webinar all success. I wish you all the best. May God bless you. Thank you very much.
Thank you, Father, for such an inspiring speech. I would now like to call Professor Deeptiman Shaha from the Department of Mathematics, St. Xavier's College, to introduce Professor Arup Mukherjee. Over to you, Professor.
Good morning, everybody. Though it should be it should be good morning to Arupda, and it's good evening to everybody. It is my privilege to introduce Dr. Arup Mukherjee, Associate Professor of Mathematics, Montclair University, USA. He was graduated from our college with mathematics honors in 1984. If I'm not wrong, he stood second in the university. Then he has done his MSc in Applied Mathematics from Calcutta University, Rajabhaja Science College campus. Then he went to USA for his PhD degree from Penn State University. After completing his PhD, he joined Rutgers University as Assistant Professor of Mathematics. Then in 2000, he joined Montclair University and has been working there till today. Professor Mukherjee's research publication, specialization in computation analysis of fluid with microstructure, liquid crystal flow, ferrofluid flow, soft magnetic elastometer, in short, in MHD, that is magnetohydrodynamics. In particular, his work investigates how flow property of liquid crystal and magnetic fluids are affected by external fields. His training is in adaptive finite element method for solving partial differential equations. His earlier work involved computation of initial data for the binary black hole problem in GTR, means general relativity, and analysis of heat transport from a heated sphere as it melts its way through a solid medium. In addition to many publications of paper and teaching numerous undergraduate and graduate courses at MSU, MSU means Montclair State University, Dr. Arup Mukherjee has taught scientific writing for engineering faculty at Tianjin University in China through the teaching in English program administered by Global Education Center. Arup was 1 year senior to me in Applied Mathematics Department, Rajavaja Science College. In our time, he was a real hero to many of us, and not only for his merit only, but in all respect. He showed us how to live the life, enjoy the life without hampering the study. So I will not take much time for this, but as far as I understand, the topic of the today's lecture, this is an application of dynamical systems. Maybe discrete, maybe continuous, and a system of differential equation, obviously. And these things we taught actually in our third semester course in differential equation. So students present here, most of you know these things. So hope everybody will enjoy his lecture. Over to you, Arup.
Thank you. Thank you, Father. Thank you, Diptivan, and thank you for Sucharita and for the large number of people that is needed to make something like this come to fruition. Nothing happens in vacuum. I am as happy as probably anyone on this call here to come back to St. Xavier's. That's where I first cut my teeth in mathematics, so to say. And it is not mathematics. The friendships that I had there, the teachers that I had there, and the life lessons that I got are things that I hold dear and try to live by. I mean, St. Xavier's is close to me. I can see Father, behind Father, that ground where we would sit around. I can think of Orunda's canteen. I can think of the cricket matches on that ground. I can think of the little delight shop by that door there. So I have lots and lots of memories. So thank you for having me. And I just want to let the organizers know that once we are done, I am more than happy to hang around and answer questions and chat with anyone who wants to chat, including students. I mean, it's early. I have time. And at that stage, if a few other people want to join the Zoom and chat, I have no issues. I mean, I'm more than happy to give that time to anyone. Okay. So I will start this and hope that things will work. Let me share my screen here. Okay, everything working? Can I get a thumbs up, Diptivan? You can see the screen?
Yes, very much.
Okay. Thank you. All right. And I am heard, right? Okay, very good. So as promised, I want to talk about some simple mathematical modeling. The idea is to involve as many of the students who have joined us, and to try and see how this process of mathematical modeling works in these kind of interesting, unique lizard species called the side-blotched lizards. More about them in a moment. What you see on the screen, that's basically my university at Montclair State in New Jersey. We are about 15 miles from New York City. So it's pretty close to where we are. And here's a place that I remember fondly, that I think of every time I go to India, which is quite often. And I would like to also give a shout out to this picture from our Freshers Welcome at St. Xavier's. For many of you who may not have met them, Right here in the middle is Father Gore. Next to Father Gore is Professor Ghosh. You have Ramakrishna Ghosh. You have read books by him. I can see Professor Maiti. I can see Professor Bhomik. And for some of you on the very right here is Kajal Bukshi. She was probably only 1 year in or 2 years into, I mean, she has also retired. And the rest of us is right there. So this is in one of the first floor rooms. And all of our classes used to be in room 31 on the 3rd floor. And this was one of the first floor rooms. So that's one of my early memories from St. Xavier's. Okay, so let's talk about mathematical models. I mean, it's just a term that says, can we use symbols to describe what we see around us? All of us know mathematical models. So there are some technical terms here. So it's an iterative process where typically you make a model, you look at the information you're trying to model, you see if the model is doing a good job predictively. If not, you modify it. So that's the normal way a mathematical model works. Mathematical models come in multiple flavors. So for most of you, you have seen dynamical systems, you have seen some simple differential equations. They can be ordinary, they can be partial. Most of you will see partial differential equations soon or later. Obviously, many models are statistical. You can have game theoretic aspects in modeling. And there are all of these terminologies, linear versus nonlinear, discrete versus continuous. Discrete and continuous means how we measure time. So dynamical systems are things that are dynamic, that they change with time. And discrete would be time is measured in steps, kind of like how you look at a sequence. Continuous would be time is measured continuously, similar to how you think of a function. So these are things that we are familiar with. You could have strategic models, you could have non-strategic model. In today's world, data-driven data analysis. There are multiple things. Some of the most common models, the most common modeling example that we all know would be Newton's laws. I mean, it models motion. So what we think of as Newton's laws, the second law, it models how things move. But this idea that models are limited is also true in Newton's laws. So if something that is moving moves too fast, Newton's laws do not do a good job of describing it. That is their relationship to special and general relativity. So basically, general relativity or special relativity, Einstein's laws of motion, if you like, under very special circumstances, when the speed of the moving body is not too high, become Newton's laws. On the other end, quantum mechanics is another limit. So Newton's laws talk about bodies with a certain amount of mass. If we think of things that are very, 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 very small, you need a slightly different modeling technique, and that's called quantum or statistical mechanics. So these are things that we are all familiar with, is what I'm trying to get at. In engineering, it's ubiquitous. So you do finite element analysis to build bridges, to build buildings, to determine cracks, to predict weather. I mean, things that are all around us require modeling. And for us, for today, the two models that we will talk about are the simplest function that we all know, exponential function. Why is it the simplest? Because that's the only function in the world that has the property that when you derive it, it remains itself. And when you integrate it, it still remains itself. No other function has that property. And the logistic model is kind of an extension from the exponential model for populations. So on this screen, the shaded portions that you see, dynamical systems, differential equations, ordinary ones. discrete and continuous models, exponential and logistic models. These are the only things that will show up in today's talk. So the rest of whatever follows will be based on this. Okay, so let's talk about overall outline. So I'll talk a little bit about this interesting behavior of these side-blotched lizards, why they're called that way. Probably most of you know what rock, paper, scissors is, but I'll briefly talk about that. We'll then come up with a quick, simple, discrete model using difference equations, discrete dynamical systems. They're the same in terms of, it's just terminology based on this rock, paper, scissors game. As we said, models are adaptive. We will notice from our discrete model that the results that we see do not mimic the data that the evolutionary behavior of these lizards give us. So we need to make transitions. We'll look at a continuous model. Some of the continuous models will still need added pieces to be able to describe the behavior. So we'll go from a linear to a nonlinear model by adding the necessary complexity. And we'll talk about the modeling process where we are careful about adding complexity. We don't add a term or make things harder just because we want to. It has to do the right job. So we'll talk a little bit about that. And that'll be it. And by that time, we will have something that approximately gives us the same behavior as we see in real life. Okay, so these lizards, they are technically called side-blotched lizards because they have black spots. You can probably see a little black spot right behind their leg over there on the picture on top, if you can see my pointer. They live off the coast of California, southwestern California, actually. So here's in red, you'll see the region or territory that they inhabit. So the Channel Islands, which are shown down here, beautiful place. They are off the southern coast of California, these little red dots here. And typically they live on these rock outcroppings. So just to orient ourselves, that's a map of the US, and we are on this left part of California. So that's where these guys lived. The rock, paper, scissors or Rochambeau game, let's think about it. So this game, you're probably familiar, it's a two-person game, and it's kind of like a coin toss. There are three outcomes: win, lose, or draw. So you make hand symbols. You either do a scissors, trying to cut things, right? Rock, something solid, and paper is like a flat hand symbol. So those are the three symbols. And the rules are that rock is strong. It can break the scissors. If you hit it, the scissors break. Scissors are strong. It can cut the paper. And paper, although it does not feel that way, it's strong. It can wrap the rock and hide it. So the game theoretic approach is rock beats scissors, scissors beats paper, and paper beats rock, which you see in this little picture over here. Through the talk, and especially in the comments, I have put multiple links, and I will share the PDF of this with Professor Roy Sucharita. And anyone who's interested can follow up on any of the pieces. There are more links in the comments. So here's a link to general rock, paper, scissors. The important thing is if two people are playing the game and one person is truly random, then, I mean, they don't have a strategy, then there is no winning strategy you can have against that person. So it's essentially like a coin toss where lots of coin tosses. So your chance of winning or losing or drawing the game. So if both have scissors, it's a draw. And then the others are the winning and losing strategies. They're all 1/3. The probability is exactly 1/3 for win, lose, or draw. there are actually world competitions on rock, paper, scissors, and many stories in popular culture. I think there's a story that says there was a referee in an FA Cup women's game a few years ago who could not find a coin, and they had the two captains play rock, paper, scissors to determine something during the FA Cup game, and was suspended because this was not part of the rules. So there are lots of these interesting sort of popular culture stories on rock, paper, scissors. Okay, so these lizards, they're playing a rock, paper, scissors. So as we'll see, the side-blotched lizards come in three colors: orange, blue, and yellow. And they are sort of in a $1 billion year cycle of a rock, paper, scissors game. So I'm going to next share a short 3-minute video that you can hear to get a sense of what these lizards are doing. So here I'll play this. Okay, so this gives us a sense of the match between the rock, paper, scissors and this picture that we see below. So what happened here? Okay, so basically here's another sort of picture of the rock, paper, scissors idea. The orange dominates blue, so orange beats blue. blue beats yellow, and the yellow sneakers beat orange. So the yellow can win against orange and lose to the blues. Orange can win against the blue and not against yellow, and so on. So it's the same story, if you like. And in terms of the offspring, they are determined by male coloration. So if there is no orange male father, you cannot have an orange male offspring. If you do not have a yellow male father, you cannot have a yellow male offspring. And this sort of cycle, no one wins. It's not they're all equally at 1/3, but it's oscillating. So when one lizard morph is higher than 1/3, the next breeding season, there are less of them. And it's been ongoing for, as you said, millennia. So we want to model this. We want to see if simple math will do the job. So how do we model something simple like this? So let's just make sure that we are all on the same track. The populations of the three morphs oscillate. That's one observation. As we heard in the video, when a particular color type or morph population is low, they produce the higher offspring the next year. So the rarer you are, the more interested the female, and there are more offspring. What happens is, so you have a maintained genetic diversity. However, the overall population remains stable. It's nothing remains exactly 1/3, but there is this oscillatory behavior without anyone dying away or all three becoming 1/3. So basically, it's a mix of mating strategies that coexist in an evolutionary rock, paper, scissors, which is the gist of what I want to share with you today. Okay, so here's an outline of the models that we will see. So we'll start with a very simple linear discrete model. When we say discrete model, there are technical terms. These are discrete dynamical systems or difference equations. The way I like to also think about these things is maybe something even simpler. If you have an equation, simple equation like x squared minus 1 equals to 4 equals to 0. There are two roots, 1 and minus 1. They're numbers. So a simple equation has numbers as solutions. If we go up a little bit, rather than numbers, if you consider what has functions as solutions, the answer is they're differential equations. So equations have numbers as solutions. Differential equations of any type have functions as solutions. And from that context, difference equations, which are discrete versions of differential equations, have sequences as solutions. So sequences are a special case of functions. Functions are things that are defined for all real variables. Sequences are defined only for the integer variables. So it's a function from the set 1, 2, 3, 4, 5, and so on. So it's a very special kind of function. It's a function on the positive integers. So the solutions of discrete dynamical systems are sequences. Solutions of ordinary differential equations are functions. And our modeling process we'll start with as simple as things get, discrete model, difference equation. We'll look at its solution. We will see that it doesn't quite do the job of predicting this behavior that we are looking for. Once we agree with that, we will try to look for a slightly more sophisticated model. And like everything in life, nothing is built from scratch or from zero. So what you do is you look at other branches of science, mathematics, where similar models, similar things have happened. So population models, where we have interacting species models. And we will take some ideas from there to see if that helps us with our question or addressing our question of coming up with a behavior for the side-blotched results. So this, the story will end with a nonlinear coupled system. So 3 equations, one for each morph, where the differential equations are coupled and they will have this oscillatory behavior that we saw. Okay. So linear models. The key idea here is we are talking about a discrete model. It's very simple. It's just like compound interest or radioactive decay, that these are things that everyone has seen. So from a money perspective, we always hear in compound interest, the more there is, the faster it grows. The more money you have, the faster it grows. In mathematical context, how do we model that? The more there is, the faster it grows. So basically, we are saying that the growth or the rate of change is proportional to amount present. If the amount present is more, the growth will be higher. So there is a direct proportionality between change and amount present. And that's what you see in this second line of the slide, that the change going from time n to time n plus 1, an plus 1 minus an, a of n represents whatever, money, some amount, any entity or any quantity you can think of. So change is proportional to current amount, an. The first equation is just saying we know and remember what proportionality means. So there is a constant beta where we have transferred proportionality into that equation. So if we look at this first equation, it can be rewritten as a of n plus 1 is, you put the beta an on the other side and you get a 1 plus beta. So in general, you come up with this very simple, basic, discrete growth or decay model, which is a of n plus 1. The amount present at the next time period is some number r, which is 1 plus beta. So r is usually a number greater than 1 when you're thinking about growth, times an. And not surprisingly, and I will spare you the details, you can check by taking this and putting it into the equation, that the general solution, remember what we said? The general solution for discrete systems are sequences. This is the geometric sequence, CR to the K. C can be any constant. This is the general solution. It's a geometric sequence. We know that when this number R is a fraction, let's say R is half, powers of R will become smaller and this will go to 0. If R is greater than 1, the powers of R will get larger and the sequence will go off to infinity. So in our normal syllabus, we see R greater than 1 is growth. And if R is between 0 and 1, it's decay. So when R is between 0 and 1, we are saying beta is negative. And when R is greater than 1, we are saying beta is positive. And you've probably seen examples of both. Beta positive is compound interest. Beta negative could be radioactive decay. So these are examples that you see. This is basic, very fundamental growth and decay model. The solution is the geometric sequence. The continuous analog of this, remember the basic tenet, change an plus 1 minus an is proportional to amount present. Look down here, the word change in calculus is derivative, rate of change, dy dt. dy dt is proportional to y is exactly what this equation down here is saying. Dy dt is some number r times y. dy dt is proportional to y. So this would be sort of the simplest form of a differential equation, an ordinary differential equation. It's a differential equation because it's an equation, it has an equal sign, and differential, it has a derivative. So the nomenclature is very, very straightforward. So this is the simplest differential equation. Probably all of you have seen a solution of this. The method is called separation of variables, and you can write out a solution. The solution to this is exponential. The exponential function, you see the exponential function r to the k here, and you'll find an e to the rt as a solution to this. So these are very basic growth and decay models. Our question involves 3 separate species. So trying to use one variable, either a or y, is not quite going to do the job for us. What we need is 3 separate variables. So maybe a variable O of t for orange lizards, a variable B of t for the blue lizards, and a variable Y of t for the yellow lizards. So we need a system of 3 variables. This you can imagine as 3 numbers, a vector. So the quantity we are studying is a vector. And for many of you, you have encountered vectors not only in physics, but also in linear algebra, where the vector gets multiplied by a matrix and the matrix vector product gives you another vector. So for some of you who may yet have seen linear algebra, I'll only say this. It's probably the most useful thing that you learn from an undergraduate education by far. You will see it in so many places in applications that it's just amazing. So if we try to take this simple equation, let me just point to it. An plus 1 is r times an, and just rewrite it as a matrix vector equation. It will look like Sn plus 1 is t times Sn, where this time S of n will have 3 things, a vector. T will actually be a 3 by 3 matrix. And again, as a reference, the solution here looked like C times R to the K, constant times R to the K. The solution here looks similar, C1 times lambda 1 to the K V1, C2 lambda 2 to the K V2. So the flavor of the solution is the same. And for those of you who have seen matrices, these lambda 1s and V1s are not arbitrary things. They are probably some of the most important characteristics of the matrix T. They are what are called the eigenvalues and eigenvectors of T. So these eigenvalues are hidden inside every matrix is some sort of inherent genetic information. Every matrix has some genetic code. One part and crucial part of that DNA is an eigenvalue and an eigenvector. So a 3 by 3 matrix generically usually has 3 eigenvalues and 3 distinct eigenvectors. I know that's not true. Some of you are screaming, no, 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 it can be repeated. I know that, but we'll just live with the simple case. It has 3 eigenvalues and 3 eigenvectors. For us, it's the form of the solution that's important. So you can obviously see that in the long term, as k goes to infinity, or as k goes to a number, so you try to take the limit of k as k gets larger, you can see that these powers of lambda, the powers of the eigenvalues, determine the long-term behavior. If all 3 of these were less than 1, then each term will go to 0. So you're going, if S of k represents a population, then it's kind of declining. If somehow the lambdas and the v's are such that all 3 of these pieces go to 1/3, you're saying that the population is in equilibrium. Each part of the population occupies 1/3 of the available space. So that's what linear algebra is. I mean, it's something that is ubiquitous: science, engineering, social science, computer science, physics, chemistry. I mean, this is probably, as I said, the most essential part of what you learn in an undergraduate. The word linear comes from linearity, and most of you know what that means. Derivatives have this property, integrals have this property. Linear algebra is linear, not because it studies lines, because it has this property. Okay, so what does our model look like in this form? So you can see the Sn+1 has orange, blue, and yellow, the three types. The population types at time n+1 depend on what happened in the previous time step, time n, O of n, B of n, Y of n. This is how the system is dynamic. You're studying the dynamics. And this is the matrix here, which comes from game theory. It's basically that the chances are 1/3 and 2/3. So this rock, paper, scissors idea, the game theoretic aspect that says that, you know, I have a chance because I am myself, and I also have a chance because I can beat 1/3 of the other population. So that matrix comes from that. We could write out a solution. So the next thing when I hit enter is supposed to not make sense. It doesn't make sense to me, so you won't be alone. So if there was an expert in discrete dynamical systems, they would look at this and say, this is not a good model. So that's what it will look like. So that's the expert's point of view. I don't know what that means. It's a bad model, and there's a lot of very difficult terms. The order 3 matrix is doubly stochastic and ergodic. So the three fixed, it's fixed points, but it has an attractive fixed point with entries 1/3, 1/3, 1/3. If we translate that into Bengali, it means every population goes to 1/3 of it. 1/3 blue, 1/3 orange, 1/3 yellow. This is the expert's point of view. I have sent in links. So one thing I have learned is when you go away from a talk, maybe all you want to know is what the hell is ergodic? What is stochastic? But the links that I have included are things like that. So ergodic theory is a branch of higher mathematics. You can specialize in ergodic theory. There are people who do. So that is information for you to find later. But just like you, when I look at all of this, this is my reaction. I mean, I don't know what it is. I'm not an expert in either of this. So my question is, if I look at something like this, can I still see that everything goes to 1/3, 1/3, 1/3 and does not oscillate? So what do I do? Let's take our point of view. Simple people sitting in class, trying to do homework and hoping that it'll get us somewhere. So I'm going to just say the long-term behavior is not oscillatory, and hard work, I'm going to solve this for many different cases. Look at the long-term behavior and see if I can see a pattern. This is what we are good at as mathematicians, as scientists, pattern recognition. So I'm going to take that equation, put it into some software, and hope that I get the answer. It so happens that discrete dynamical systems, you can solve them in 2 minutes if you know a little bit of Excel. You don't need anything more than Excel. So if you want fancy software, that's fine, but those equations, they basically can be put into Excel and you can come up with solutions. So what you'll see is things I did on Excel. And I'm happy for students to talk to things about, what kind of software is available, what can you do with these things. That's really where part of my expertise is. So the only thing is, when you're doing computation, pause and remember about the only thing that separates us from AI and robots and computers, right here, our brain. Analyze, think, Don't forget about that. So I'm going to put things into Excel and look at long-term behavior and share what it looks like. And the key lesson that we'll come out with is there is no oscillation. So it's not a good model. Okay. So do all roads lead to Rome is the question. Do all initial populations lead to 1/3, 1/3, 1/3 with no oscillation? So let's try a simple thing. Here's a simulation where half the population was yellow, 0.5, 1/3 of the 0.3, 30% of the population was blue, and the remaining 20% was orange. And we let this model run, and you can see that after 5 or 10 generations at most, the model sort of settles what this expert opinion was giving us, that there is no oscillation. There was a little bit of up and down, and then things settle down. So there's this equilibrium at 1/3, 1/3, 1/3. So 50% yellow, 30% blue, 20% orange. After a few generations, 33% of each. Let's look at one other simulation. I'll let you look at it. This should look even more dramatic, that this is not a good model. We started with only 5% yellow and blue and 90% of these dominant orange guys. And after 10 generations, 1/3, 1/3, 1/3. So this model is not doing what it is supposed to do. So basically a very small proportion of sneakers and maid garters, the blue and the yellow, easily catch up with a much larger proportion of dominant orange moves, is what this model is saying. And at this point, my thinking mind is saying, something's wrong. I mean, I don't like this model. One more experiment, and this one clearly says it's terrible. Notice what I start with. No orange lizards in the population. Remember that orange can only be born from orange. And what does the model give me? Now I have 1/3 of orange. This is clearly wrong. So the model is not doing its job. So here, I mean, my surprise has turned to, please, let's find another model. So no orange dominance can still give rise to them in the future. So we need a different model. And what do we do when we need a different model? We ask the questions, what do we need to change? And how do we implement that change? So this is a process that you should look for in your undergraduate education. Mathematics is natural and teaches you this. This is a life skill that you'll need no matter if you're working in the financial sector or teaching or working in industry or doing whatever. So this process of thinking, getting information from other sources, putting them together and packaging and coming up with something that is yours is exactly what modeling is. It's adaptive. That's what you do. So we first note that rather than the discrete, we can try the continuous version, same problem. We will see the same behavior of settling to 1/3, 1/3, 1/3. So here's the process. Has someone else addressed similar questions somewhere else? Which parts of these models are okay? What restrictions should we think about? So these are general questions one needs to ask whenever one comes up with a model. This is exactly, I mean, I don't know exactly, but I would assume this is how the greats came up with their great models that we call Schrödinger equation, or we call Newton's law of motion, or Einstein's law of relativity. I'm sure there was a lot more than this simplistic version. There was a lot of genius involved there, but the ideas are similar. History tells us that. So we basically take some information from other pieces put it together. So let's do that for the last maybe 10 minutes that I have. So I will start with our exponential model right here. Exponential model gives us unlimited growth. So if I think of an exponential model trying to give us population, it's not very sustainable. There's no species that can keep growing without being cognizant of the environment. So for example, us, we have all of this talk of how many of us can the earth sustain? How many crops can we grow in Haryana? How many tigers can the mangrove forest sustain if the mangrove forests in Sundarbans keep dwindling? So these are all questions about capacity of the environment that we live in. So you have a population, what's the capacity of the environment? So this exponential model is unlimited growth. This so-called logistic model, you'll notice that it's the same if you take this second term, this term I have marked here, if you throw that out, it's the exponential model. So there is this term, this second term here, the quadratic term, y, the negative yt over c times yt, which is it's a negative term, which is saying the rate of change, ddt of yt, the rate of growth or the rate of change, is being inhibited or retarded by this term. It's a negative contribution. It lessens the rate of growth. And it's basically saying that C is the capacity. So it's basically saying if you're at this limit, that there is, what the second term is 0, there is a lot of space, you're peaceful, you're happy, you can grow as much as you want. Mental, physical, all the space is yours. When you incorporate the term, you're basically saying it's crowded like the subway at 9 a.m. at Central, and everybody wants their little space. So the second term talks about competition. The first term is basically exponential growth. Here's another view. So if I solve just the exponential model, exponential growth. So this is a solution for a simple exponential model. For those of you who have seen this would be a direction field that solves an ODE, and these would be solution curves corresponding to specific choices of initial conditions. So this would be, I guess, a phase plane, something like a phase plane plot. Okay, so this would be an exponential model. The corresponding logistic model with a capacity of 100 would look like this. So if you look at the logistic model, each curve starts off looking like the exponential curve. So the red, blue, and the light blue curves down here, they start off looking exponential. At some point here, which corresponds to half the carrying capacity, the concavity changes. So it changes from being concave up to concave down. So basically the second derivative changes sign. And in the limit behavior, as time goes off to infinity, you can see that the capacity, capacity line is an asymptote. It's a horizontal asymptote. So this is what is logistic model. So basically, this is what we were saying. So let me go back here. In the early part, the exponential term dominates. The exponential behavior dominates. In the later part, the competitive behavior dominates. Okay, and that's what you see here. In the early part of the logistic graph, it feels like the exponential curve up top. In the later part, it slows down. The rate of change slows down until the rate of change becomes very flat. So this is related to the Earth's carrying capacity, for example. How many of us can live on Earth? How much can we grow? I mean, these are questions that are important questions. So same statement, competition inhibits growth rate. As saturation of the population increases, when I say saturation, when you get closer and closer to capacity, that's saturation. Normal, simple English words, the growth rate will slow down. So the closer you are to capacity, the slower you grow. This is all smart populations know what is good for them. That's what the logistic growth model is. Okay. All right. So here is the logistic, not quite the logistic, a version of the growth model with competition for two species, not quite for our lizards yet. So if you look at the equations on the left, each equation would look like the logistic equation we just saw, almost. They have the same flavor, but they're different. The first term is the same. The second term is a competition term. Rather than N1, which was the competition which was between ourselves, the same species competing with itself. Rather than that, we now have an N1, N2, a product term, which is competition within the two species. So you can imagine this is, you have a little forest and you have foxes and rabbits. The foxes eat the rabbits for food and the rabbits eat leaves. So what do you think happens when there are less rabbits? The foxes die. When there are fewer rabbits, more foxes die. They die of starvation, competition. So that's what this second term is, this N1, N2 term with some constants and some capacity. That's what it tells us. So this is, again, there are lots of references for this for you to look at, and I can talk about this for anyone who has a question. This is what is called a simple Lotka-Volterra competition model, two species competition model. And if you look at a solution of this, you get this oscillation behavior. So one species goes up, the two lines here talk about a predator and prey. These foxes and rabbits I was talking about. Okay, so this is a typical competition model. We have now found what we are looking for, oscillations, competition. And that's what the lizards have. There's one other step here. Again, we are not going to build stuff out of nothing. Oops, sorry. Okay. So there are these two separate growth models. One is just the exponential and one is the logistic. So if you have the exponential and you add competition, you get this Lotka-Volterra model. But if you take the logistic and you add competition to that, you get the model that I want to focus on, this model on the right. So the one on the left, it's just exponential. The second term is competition. The one on the right, the first two terms gives you logistic, and the dark bold-faced term, competition. The bold-faced term is similar to the term on the left. The bold-faced terms here are N1, N2, N1, N2 product terms, competition terms. They're interspecies competition. This N1, N1 term or N2, N2 term is self-competition because it has to do with the fact that you have limited capacity. The closer you are to capacity, your growth rate slows down. So it is self-competition, fighting for space on the metro. Both of us are humans. And this one is some alien has come in and they also want the best seats on the metro starting at Domno. So it's a matter of which kind of competition. We are almost there. Side-blotched lizards, yellow, blue, and orange. The A's, A1, B1, A1, B2, C3, A11, these are some numbers, but focus on the model. The model, the first two terms, it's a quadratic, a YT term and a negative YT squared. And the third term is an interaction, Y versus O, yellow versus orange. Let's go back here. The first two terms, N1 and N1 squared, quadratic. And the last term, N1, N2. So first two terms are, so now we are exactly thinking, we are back to thinking like mathematicians, like, you're only focusing on the basic structure, quadratic and a competition, quadratic and a competition. So it is almost like left alone, the yellows would have a logistic growth. That's what the first two terms tell us. But now they have competition from the orange. So there is this competition term. The blues would have a logistic growth, competition from the yellows. The orange has logistic growth, competition from the blues. And the coefficients can be chosen appropriately based on data to make sure that we can, we are doing justice to the experts in biology and the experts in ecology and the different experts who actually study these beings and have ways of telling us mathematicians what this behavior is. Once all of that falls into place, we go back and we say, if I solve this, am I going to get the oscillatory behavior of rock, paper, scissors? And so we have done our job assembling the correct pieces. As mathematicians, this is what we are good at. Logical thinking. Take different pieces from everywhere, make sure the logic is right, fit it together. And this is the skill that employers want from us. This is why mathematicians are also hired as Wall Street people. Mathematicians can work in multinational firms. So this is really the skill that people are looking for. And at least in this case, I hope it worked. So here's a little bit of proof that with the right data, I don't know how visible the lines are. The yellow is probably not visible. There are 3 lines, I promise you, yellow, red, and blue with different initial conditions, and you should be able to see the oscillations. So for example, on this graph on the northeast corner, when blue is high, blue goes down. When orange is low, orange goes up. When yellow is low, yellow looks like it's going up. So it is this oscillatory rock, paper, scissors. Okay, so there is always more to the story. I hope that what we have talked about is something that makes you curious, makes you interested, makes you want to do something, makes you want to do a little bit beyond just passing an exam. I mean, it's more fun. Passing an exam and getting 90% is not so bad, but it gets boring. I mean, just studying, if you want to challenge your mind, play with things that don't have answers. Exams have questions where there is always an answer. The fun is when the answer is unknown. That's when the journey is fun. So that's the end of the talk. Thank you very, very much to everyone who organized and everyone who's here. As I said, I am more than happy to answer questions and stay as long as you guys want. So I'll stop sharing the screen so that you can see me again. I think I did that on reasonable time, right? Did that, Sujata?
Yes, sir. Definitely.
Thank you. Anything, any discussion, any question, anything?
So I got a few questions.
Sure.
Question number 1 is, what can be the possible restriction on the model we have learned?
Many. It's too simple. I mean,
Yeah.
This is too simple. I mean, there is no spatial variables, first of all. So, I mean, the lizards, there is some spatial distribution over the large territory, right? Once you put spatial distribution in, you're thinking of the lizard population as not only a function of time, but a function of space. And you're putting in the density, the population density. So now you do not have an ordinary differential equations, but you need partial differential equations. And coupled systems of PDEs are,
yes,
I would say, exponentially more difficult, easily. So, I mean, every time we model, we are putting in restrictions. The only thing is you try to focus on specific observation you're trying to model and hope that you get somewhere close.
I think one more thing is all these equations you are taking is autonomous system.
They are.
Is there a possibility that these are non-autonomous?
Well, depends on the population. These are protected species.
Okay.
The study and the data comes from the Channel Islands. They're protected and people are not even allowed to go near where these lizards are. I mean, they have been doing this for 10 million years.
Okay.
They're not being bothered. They are given free rein. So, I mean, there are other places where there has actually been changes. So there have been different places where the blues have actually dominated, have won. So there are follow-up to these. So there's always more to the story. But this particular data, I mean, and I also want to be very clear. I wouldn't call this research. This is something I would call, this is for undergraduates to pique their interest. If I was doing this as a research problem, I'd be a lot more careful with my answers and with the data and with the coefficients. So this is just to give a picture of what is possible. I mean, I wouldn't say call this as research. I mean, undergraduate research involving a couple of third semester students to say, please run the data, make them, is what this project is. So that's the kind of thing I think it's great for.
So I have a second question is, should not the logistic model be the right model that stabilizes the population at the end?
Right model, yes, there is capacity. So without capacity, I mean, who grows without bomb? Yeast culture, bacteria, coronavirus, it seems. So those are the only exponential growths right now. So obviously you need some capacity. Is a simple carrying capacity the right answer? Actually, there is a fascinating follow-up on this. And this, so if there are students, we can talk about maybe even possible collaboration. So there was a paper I read. What is the Earth's carrying capacity, human carrying capacity? I've given a reference to this paper. It's a paper in Nature. It uses just a logistic model, so it does not require any fancy math. And it says, how do you even determine what determines Earth's human carrying capacity? And how close are we to it? How has it changed over time? Agriculture has improved, so we can feed more people. So obviously, the carrying capacity curve is not a straight line. It itself follows some logistics. So there are these.
So it's not a constant.
Exactly. So the C in the logistic model itself is a function of time. Which probably follows another logistic model. And analyzing something like this and matching it with real life data is, I think, a great project for students. Because this is something they can do and it can intrigue them. And the answers are hard. Not necessarily known. They are simple questions with interesting and hard answers.
Another question I have, when you use the eigenvalues in the mathematical model, is it possible that we obtain an imaginary solution for a real life problem? I think the answer is yes.
The answer is yes. The answer is yes. It would mean that we are using a bad matrix. No, you won't get the imaginary solution. What will happen is
not imaginary solution. Eigenvalues are imaginary. Actually.
Yes, but as long as their real parts have the right modulus, so as long as they live in the unit circle, the long-term behavior, those two will go away, and you'll settle to the third one when k goes to infinity. So you'll settle to the one with the maximum magnitude, and hopefully the other two will go away. So this is sort of the essence of higher linear algebra. Greshko-Rinne circle theorem that says that, matrices with certain properties will have all eigenvalues in here, so the long-term solution will go to 0. So if there are imaginary eigenvalues, which 2 of them can be, and sure you can have that, but they'll have the right long-term behavior. those two components will go away. And you'll settle to the third eigenvector, the one corresponding to the real eigenvalue.
Another question I got, is this model actually a broader version for the real life food web acting as a loop and is probably for all chain in the same, or is particularly for the lizard? That means I think the person
this is
yeah.
clearly particular. I mean, the adaptive idea is always true. I mean, whatever you do, you look again and say, did it do the job? And you use a feedback loop to come and improve or change the model to get the right answers. I don't think the right answers is, I mean, or to answer the right questions. I think that's a much better result.
I think here actually competition, intraspecific competition, interspecific competitions, those are there. So that model can be extended.
Sure.
That model can be extended in that way.
Those essential things can be extended.
Yeah, that can be extended, but not this particular model. Another question I have, finally, you showed us a equation, a system of differential equation for 3. And there, those A11, B11, etc., those coefficient matrix, is it actually same as the earlier one? That one.
No, this is a nonlinear system, so you cannot put in the matrix. This system had the interspecific, so it's clear it's nonlinear.
Okay.
I mean, it had two quadratic terms, so matrices are not going to do the job.
Okay. Yeah, but I think that can be used as a quadratic form.
There is no formula to solve it. You have to solve it numerically, and you have to basically linearize across near fixed points. I mean, you have to work a lot harder to solve.
Okay. So those coefficients can be find out experimentally. How we get that coefficient?
They come from data. Exactly.
Okay, so from data we get that coefficients.
Exactly.
The real data, or from those islands.
Whatever. I mean, papers.
Yeah. Okay. Thank you. Over to you, Shajid. No more question.
It was an amazing lecture, followed up by some equally amazing questions. Thank you, Dr. Mukherjee, Professor Shaha, and all the attendees. I would now like to call Professor Sucharita Roy, Head of the Department of Mathematics, to deliver the vote of thanks. Over to you, Professor.
Thank you, Shajid. A very good evening to one and all present here. As we come to the end of today's event, I deem it a great honor and privilege to propose the vote of thanks for this international webinar to this August gathering. First and foremost, I would like to thank Father Principal, Reverend Dr. Dominic Fabio, S.J., for delivering the welcome address in today's webinar. We are grateful to Father for his words of encouragement and unstinted support. Father's able guidance, kindness, vision, commitment, and exemplary leadership has always been an immense source of inspiration for all of us in striving towards excellence and imbibing the very motto of St. Xavier's, nihil ultra, nothing beyond. It is indeed a privilege and a moment of pride for me to thank Dr. Arup Mukherjee, the speaker for today's webinar. I'd like to express my heartfelt thanks and gratitude to Professor Mukherjee for accepting our invitation and delivering this intriguing lecture on this very relevant topic. Dynamical systems can show how a complex self-regulating system can emerge from the interaction of a few variables, and studying different dynamical systems is indeed a challenging job for the mathematicians and an exciting one at the same time. Thank you, sir, for showing us the way and enlightening our students with your vast knowledge and experience. I would like to take this opportunity to extend my gratitude to Professor Bertram De Silva, Vice Principal Arts and Science, and the Deans, Dean of Science Dr. Topati Dotto and Dean of Arts Dr. Orko Banerjee, for their constant support and guidance. My sincere thanks to the support staff and the technical team of the Computer Science Department for their invaluable support and help in smooth execution of this event on this online platform. I thank Professor Arun Chandra, Member Secretary Academic Council, and Professor Parthopratim Ghosh, IQAC Coordinator, for their valuable suggestions for the successful organization of this event. I owe heartfelt gratitude to my esteemed colleagues of the department for their wholehearted support, hard work, and contribution in making this event a grand success. Last but not the least, I thank all the student volunteers of the organizing committee for putting in such concerted effort repeatedly and making the webinar a resounding success. Special thanks to the Master of Ceremonies of the event, Shajujjo, for emceeing the webinar beautifully. I would also like to thank Obhik for his efficient system handling, Shomita, Fatima, and Rishiraj for coordinating the Q&A session without any glitch, and Ritik for making such a wonderful poster for this webinar. Thank you all. I thank my beloved students for attending this webinar and all distinguished invitees who have graced this occasion by their august presence. I owe a special gratitude to DS Sir, who initiated this very idea of organizing this international webinar and guided us throughout this journey. Thank you, sir. Once again, I thank one and all present here. Stay safe and well. Good night.
Are there any other questions or informal things that the students came up with?